Welcome to the final presentation for EEL6825, Group 16. Our project explored optical character recognition of handwritten digits. We explored three different algorithms: PCA using Bayesian and Gaussian classification, histogram modeling, and neural networks.
Hello, my name is John Groner. Today I'm going to present the PCA results for Group 16. These are the first 25 principal components or most significant eigenvectors achieved when principal component analysis is performed on our training data. If an incoming image is then multiplied by these 25 vectors, the result is a projection or 25-point vector that represents that image. That 25-dimensional point in space can then be used to perform k-nearest, Bayesian, or other types of classification. Once projections of all of our data are achieved, then we can perform k-nearest classification or Gaussian modeling with Bayesian classification on all of our data. These charts show the results when 80% of our data is used as training data. As you can see, the Bayesian classification with Gaussian modeling outperforms the k-nearest. When our gold data was run, we ended up with a 99% data error and a 6.08% test data error when Bayesian classification was used. The next slide shows some properly classified images, and as you can see, the images came in and the projections when used to reconstruct the image actually produced a better image. This next slide shows some improperly classified images, and as you can see, the original images are on top and they weren't very clear to begin with, so then when the first 25 most significant eigenvectors were used to rebuild the image, it wasn't as clear.
My name is David Sharp, and I'll discuss the neural network method for classification of our data set. For the neural network, I used the MATLAB Neural Network Toolbox for all development and design. I used the new FF function to create a neural network, the train function to train the neural network, and the sim function to test the neural network. In order to design the network, I experimented with different parameters of the network, starting by setting the network to all default parameters and then varying a single parameter to determine the optimal parameter for classification. One of the first parameters I experimented with was the number of hidden layers in the neural network. I experimented with no hidden layers, a single hidden layer, where I varied the number of neurons in that single hidden layer from 1 to 16 neurons, dual hidden layers, where I fixed the number of neurons in the first hidden layer to the optimal number found in the single hidden layer experiment, and then ran 1 to 16 neurons in the second layer. I determined the best performance for our particular application to be no hidden layers in the neural network. This slide shows the error per digit through the neural network. As you can see, the network did very well with digits such as 0, 2, 3, and 6, but then the error started to creep up some with digits such as 1, 4, 5, 7, 8, and 9. Here's an example of where the network was not able to classify the digit correctly. The image shown here is a 5, but the network determined it to be a 3.
Hi, my name is Mike Gideons, and I'll be talking about the histogram modeling we did. The histogram modeling algorithm was developed with 4 knobs and 2 decision rules. 54 unique modes were chosen for a comprehensive run set for the histogram modeling algorithm, as shown here in the run matrix. Within the run matrix, 3 groups of columns indicate the image size. Rows in the run matrix indicate the morphing used. The rows are grouped into 2 sets, each indicating the type of centroid generation used. The columns of the run matrix indicate the number of centroids used. Lastly, each mode resulted in 2 error rates, one calculated when using the Bayes decision rules based on the log likelihood, and the other one using the ground distance measurement for histogram comparison. Here is a snapshot of some of the data that was collected from the run set. The data was logged autonomously by a wrapper that repeatedly called the histogram modeling algorithm. This is the error rate for the classification of the test images only. In summary, for the histogram modeling, a total of 297 runs were made, with the first 27 modes being run 10 times each and the results averaged. The best performance achieved was 15.51% error rate on the test data. And the biggest surprise was that the fixed grid centroid generation outperformed LBGVQ. And finally, a comparison of all 3 primary forms of classification was made. The databases used for training and testing each of these classifiers was the same. MATLAB was then used to time both training of the entire training dataset and the classification of a single-digit image. This concludes Group 16's presentation.